So before going to the analysis part, we will see various kinds of errors. So one is single bit error. After that, we'll see what is burst error. Example, let's say your input is 0101 and you are sending through cable. What might happen? So this 0 might become 1 and 101 will safely reach. That is one of the possibility. Then we say that there is only one bit corruption, that is single bit error. Similarly, we can define 2-bit errors, 3-bit errors, so on. Now what is burst error is? So burst error is error where there is more than one bit gets corrupted. Example 00000 if you send, and here you are getting, let's say 11100, then we say that it is a burst error because there are 3 bits which got corrupted, right? Now similarly, if I send 00000, what might happen? First bit might get corrupted, then second bit 000, let's say last bit is 1. Then here we can say that there are 2 single bit errors, that is one possibility. But we don't know the reality what happened, but this might be a long burst error also. Sir, how can we say that it's a burst error? There are these 3 bits which did not get corrupted, right? How can you say that? I will tell you. For that you should know the story actually how you get burst errors. Example, this is the area where you are getting the noise in the cable, especially for microsecond of time. In that microsecond of time, all this 1 2 3 4 5 bits are going to propagate it. Okay, that is what our assumption. So within microsecond of time, if only these 5 bits are going to propagate, then that burst error might affect these things, right? Now especially 0 means one signal. So this noise may not be, may not affect everyone same, right? Example, so imagine this situation. There is a road accident and there are 4 people and they are in that car, and because of that road accident, if let's say this car is hitting some hard point, then do you think that everyone gets affected in the same way? No, right? In the same way here also, if 5 bits go through this one, then what can happen? This kind of thing might happen. How you say? 0, let's say seriously damaged, 0 become 1. But these remaining 3 bits did not get such damage because at that time this noise might not have very strong, influence, I can say. So these 3 bits again got damaged, but your receiver was able to understand that still it is as 000. That is the way you get this kind of pattern. After that, what happened? So this now your distortion noise again affecting seriously this last bit, it might happen, then that 0 becomes 1. So finally, because of your noise will have some unexpected behavior. We don't know how it affects the bits inside the message. So that's why this kind of thing also can happen. That's why in theory what we say is burst error. How to identify burst error is very simple in the theory. So in this entire pattern, first bit wherever it gets affected, mark it, and the last bit, so see the huge span, this is the last bit where it got affected, right? In between anything can happen, don't worry. Then we say that 1 2 3 4 5, this is the 5-bit burst error. But in the reality, this might be the second case. What is that? There is a small noise 2 times, but in between there is no noise. Because of that also these 2 bits might get corrupted, right? So but we don't know what is happening in the reality. That's why safely we assume that there is a long burst error. Because of that these many bits are getting corrupted, though actually they have not corrupted, correct? So in theory, let's define burst error is like this. Burst error is nothing but an error where the first bit and last bit in that burst definitely got corrupted, but in between we don't know, because we are just simulating the real time behavior. In the real time, generally this kind of situation happens. What is that? Because of the noise, few bits gets corrupted but not all. That's why we define burst error like this. Let's summarize. Single bit error. From now onwards, because we can't predict what is noise and where it is affecting, so simply we say that single bit error is a error where exactly one bit is getting affected. Second one, burst error. Burst error is nothing but an error where some block of bits are getting corrupted, but I need not be all the bits in that block, but definitely the first block bit, definitely the last bit. This is called burst error. So now, so in the reality, you might get single bit error, otherwise burst error. Now we'll come to our polynomials. So we are going to use polynomials to detect this kind of errors, right? So what I want to say is 99% of the time, So you get burst errors. Very rarely you get single bit errors. The reason, so whenever you get burst, then the duration will be microsecond at least, right? But within microsecond of time, lot of bits are going through this noise. That is what the real trend. That means within microsecond of time, because of the speed of the bit, first of all you should know what is the speed of the bit. This is your signal, right? So signal will have generally light capacity 2 into 10 power 8 meters per second, and let's say this is the area where you are getting noise, and the time is microsecond of time. Within microsecond of time, lot of signals can go through it if you send them. So generally that range will be 100 to 10,000. So though noise is for very small amount of time, but within that amount of time, so because of the signal speed, large number of, otherwise huge number of bits will go through it and they will get affected. That's why 99% of the time burst errors occurs. Example, imagine there is a highway. In that highway, so you are just keeping one stone only for 10 minutes, but within 10 minutes of time hundreds of cars will go through it, correct? Then they will hit it and they will get corrupted. That's why, so though this 10 minutes is very small in your time period, but it will affect lot of cars, right? Similarly in communication medium also, though your noise time duration is microsecond, that can affect lot of bits. That's why burst errors are very common and single bit errors are very rare. That's why your polynomial which you are going to discuss should be able to identify burst errors very effectively. We will see that theory now. Now we'll see the code words and single bit errors. Whenever single bit error occurs, then what will be the resultant polynomial? Example, let's say you have a code word like this 10010. Then what is the actual polynomial for this one? So it will be like this, right? 0, 1, 2, 3, 4. So x power 4 plus 0 into anything is 0, then only once we have to represent, right? X power 4 plus x power 1, you know it. Then the resultant code word, if you see x power 4, because this bit is not corrupted, but you got one more one, you see, that is nothing but 0, 1, 2, 3, 4, x square plus x. Now what I want to say is, so in code word you get extra word, right? Otherwise extra term. Sometimes some terms you will be losing. Example, x power 1 is what? 1, right? If that 1 becomes 0, then this x power 1 will be missing here. Okay, so we'll see that. So finally what I want to say is, whenever, only focus on that single bit error. Whenever there is a single bit error at third position, 0 and 1. So when this 0 becomes 1, on behalf of that you got one term, right? That is x power 2. So what is the significance of that 2? We will see, because the position is 2, right? Now we'll see here one more single bit error. 10010, 10000. Then this is the position where you have single bit error. Then but here the difference is 1 becomes 0. Now again we observe what will be the resultant polynomial. So what is the polynomial here? 0, 1, 2, 3, 4, right? So x power 4 plus x power 1 become x power 4 plus anything? No. So x power 4, right? So finally what I want to say is, sometimes you in the resultant code word, some of the terms sometimes missing, sometimes they are coming, correct? So that is one observation. Now let's write here code words plus error. That means, so you are sending the code word, then you will be getting code word plus some extra. What is that? Error. So why? Because of the error, so something is missing. So what can I say is, in your code word there is some error. So that error also can be represented as polynomial. We will see that. Example, so your code word was x power 4 plus x, right? But you got x4 plus x square plus x. Then we can write that as x power 4 plus x power 1, which is your actual code word, plus error is x square. Now we'll see here. X power 4 plus x power 1, this is your code word. Then you got only x power 4. Sir, how do you separate it as code word and error? I will show you. So your code word x power 4 plus x power 1 and the error is x power 1. Just add them, you will understand. X power 4 plus 2 into x power 1 is 0, correct? So 2x is 0, then you get x power 4. That means, so this code word can be written as actual code word plus error, correct? So finally every time whenever we have a code word, we can write it in a form of code word plus error after sending after sending, correct? So you remember a thing. One more time we will see example. Let's say you have 0 1 0 1 0 0 something like this and 1. Okay, this is your actual code word. Now after transmission what happened, you got 1 1 0, let's say 0 1 0 0. Okay, now we'll see 3 plus 4 7, 3 plus 4 7, correct? Now we'll see whether it is single bit error or burst error. 1 1 same, 0 1 1 0, yes, lot of errors. This is the first position, correct, where you got error 0 and 1. Now if you continue 1, there is again problem, 0 same, 1 same, 0 same, 0 same, yes, there are 2 bit errors, correct? Otherwise this is a burst error from second position to third position, a 2 bit error, otherwise burst error of size 2, isn't it? Now what I am going to do is I am going to write polynomial for actual code word and false code word. This is false code word, right? So first of all we write code word for polynomial for this actual code word. X power 0, x power 1, x square, x cube, x power 4, x power 5, x power 6, isn't it? It would become x power 6 plus x power 4, see only once we should write, right, x square. Now false code word if you see, that is x power 6 plus x power 5 plus x power 4 x cube x square, isn't it? So this is your false code word, correct? Now this false code word can be written as actual code word plus error. Let me write it. What is your actual code word? X power 6 plus x power 4 plus x power 2. But your false code word is x power 6 plus x power 5 plus x square. How to convert it to error plus actual code word, we'll see. X power 6, first of all write actual, x power 6 plus x power 4 plus x square. What is our target? We want to get this one, because we want to write this in the form of actual plus error. So what would be the error so that you get it back? Simple. In the actual code word you have x power 4, correct? But you don't have here x power 4, that's why add x power 4. Then x power 4 x 4 will be cancelled. Our target is getting this one. So x square we have, don't write anything. X power 6 we have, but x power 5 you have, then add x power 5. Slowly you understand. What I want to say is this is nothing but x power 6 plus x power 5 plus x square. Just simplify and see. Now I separated that your false code word into two parts. This is your actual code word. See 642 actual. So the entire thing is false. Then what is this part? Error. So there is a error polynomial. That means your error also can be represented as a polynomial. Because this error is added to your actual word, that become a false word. Understand? Now every time from now onwards, once we set the code word, then whatever we receive, that received word can be represented as actual code word plus error. Remember it. So using this we are going to do the analysis, right? So these are all various examples saying the same thing. Understand? Now one more thing I would like to tell here, x power 4 and x power 5. What is the significance? What is the significance of error we will see. So in this one, what is the error? Error term is x square, remember it, correct? Now here what is the error term? X power 1, correct? So sorry, here error term is x square in the first one, remember, forget about this one. You come here, here you see the error term. So the error term is x power 4 plus x power 5, correct? So x power 4 indicates fourth bit, 0 1 2 3 4, remember it, mark it. And x power 5 fifth bit. See, if you carefully observe, since 0 is modified to 1, 1 is modified to 0, that's why this x power 4 plus x power 5 are coming to the error. So that is the shortcut. From now onwards, I don't require to do this all these things. Directly by observing what are the bits got modified, their representation we have to write. That's it. Okay. Now we'll see that. Let's see one more example. In this example, first of all, what is the polynomial? The polynomial is x power 0. Here x power 1 x square, x cube, x power 4, x power 5, x power 6, x power 7, x power 8, x power 9. Then if I write it, x power 9 plus x power 7 plus x power 6 plus x power 4 plus x cube plus x power 0. This is your actual polynomial. You sent over the cable and you got this one. So there is a burst error. We will see that burst error. 1 1 same, so that is not part of burst. Then 0 and 1 there is a difference, it's a part of the burst. Now we'll come from right to left for easy calculations. See, 1 1 same, so it's not part of the burst. 0 1, so it's a part of the burst. That's why this is the largest span where you got some of the bits corrupted, right? That's why I can say that, I mean, already I told you in the burst everything need not be corrupted, so this is the burst, I can say. Now the question, this polynomial is not actual polynomial, this is a false polynomial, but this false polynomial, let's say false polynomial or error, I mean false polynomial, this false polynomial equal to, this is, let's say, actual polynomial, correct? So always we can write it as actual polynomial plus this error polynomial. So this error is because of the cable, right? So we will see whether we can write it or not one more time. Of course, we know that we can write it, but I will tell you first of all shortcut because of our observation. After that, we will go to the regular procedure. So shortcut is very simple. In the burst, whoever got modified, whatever the bits got modified, then corresponding to that bit, you get one, I mean, term in the polynomial. So error polynomial contains, we will see. Since just go to error burst, in the burst 0 to 1, there is a modification, right? What is the position? X power 8 plus. Now x power 7's position not modified, it will not be added in the error term. X power 6, yes, got modified, then add it. Whether it is 1 or 0 doesn't matter. Now there is a transition, see, x power 5, 0 to 1, isn't it? So for easy calculations, let's write weightages here also. X power 9, x power 8, x power 7, 6, 5, 4, 3, 2, 1, right? Now 6th position, there is a difference, add it. Now 5th position, there is a difference, add it, isn't it? Next 4th position, same, don't add it. 3rd position, you add it. 2nd position, add it. 1st position, 0 1, there is a difference, add it, correct? Now this will be the error term. That means what? I will tell you. So this polynomial, if you represent, that can be that also can be represented as your actual polynomial plus error polynomial. So that means if you add this polynomial which is actual to error, you get your false polynomial. We'll see why. First of all, so what we do is we write we take the false polynomial. What is false polynomial? X power 9 plus x power 8 plus x power 7, right? Then x power 5 plus x power 4 plus x square plus x power 1, isn't it? So this is your false polynomial equal to, what is your actual polynomial? X power 9 plus x power 7 plus x power 6 plus x power 4 plus x cube plus x power 0 plus error. So this error, definitely this one. I am going to give some intuitive reason why this error will be this one. Simple. So just see the reasoning. X power 9 you have in the false polynomial, in the actual polynomial also we have. Why? Because there is no error. So there is no error in the bit, that's why nothing should be added to the error. If you add x power 9 here in the error, then x power 9 plus x power 9 will become 0. That means what? X power 9 term will be disappeared, but we know that in the actual polynomial it is there. That's why what I want to say is, whenever you have x power 9 in actual polynomial and false polynomial, then error cannot contain it. Remember it. Next. So in your false polynomial you have x power 8, correct? Yes. But in your actual polynomial there is no x power 8. That means what? Definitely to equate them, here we have to add that, isn't it? That's why. Then only it will be equal to your false polynomial. That's why always x power 8 comes into the error term. So finally one more transition, you see, this is 0 to 1, right? Similarly for 1 to 0 also we can give the same reasoning. That means whenever a bit topples, then we have to, I mean in the polynomial language, I can say that one term should be added on behalf of that. Example, whenever x square 0 to 1 there is a transition, that means definitely error term contains x square. That's it. If you remember that, then we are going to do very good analysis about this polynomial generators. Okay, now we'll formalize everything. So this is your code word c of x, which is a polynomial. So generator is nothing but a divisor polynomial. Let's represent it with g of x, and transferred word is c of x plus e of x. We know that, where e of x is nothing but error word. So we know that transferred word can be represented as actual word, which is nothing but code word plus error word. Now using this theory, so we are going to identify the properties of generator. That means what kind of generator will be good. Slowly you will understand that. So first of all, let's say focus on the transferred word. Take the transferred word C of x plus E of x. Mr. Transferred word. So we are going to divide you with g of x, right? You tell me what is the remainder you are going to give. That is also known as syndrome. We know the idea. We are going to divide this c of x plus e of x, which is nothing but transferred word, with g of x, and the syndrome is nothing but remainder. If it is 0, then we can't identify whether it is error or not, correct? So before that, whether it is remainder 0 or not, we don't know, but we can do like this. According to our polynomial division, c of x plus e of x by g of x is nothing but, we can say that c of x by g of x, that means we are dividing c of x, then e of x also, correct? So that is quite, general arithmetic. Now, since this code word is original code word and we already divided that using generator and we got remainder 0, then if you focus on reminders, then you get here remainder 0. I am talking about syndrome. What is the syndrome you get because of c of x by g of x? 0, right? Plus. Now, whatever the syndrome you get, non-zero syndrome, if and all if you get, it is because of this component. If error is divisible by g of x, then you get syndrome 0, and if error is not divisible by g of x, then that is non-zero syndrome. Now, what is your wish? What do you want to have? So, obviously, this part will be divisible by 0. Now, really you want to detect the error. Assume that, let's say there is an error. Really there is an error e of x that should not be divisible by your generator. If you have an error and that is divisible by generator, then what? So there is an error, you are identifying it as so. Then what happens? This also gives syndrome 0, 0 plus 0, 0. Then you get syndrome 0 overall. That's because your error term is escaping from the process, correct? So that's why it's all now g of x responsibility. Your g of x somehow should not divide e of x. That is what my wish finally. For that I should carefully design g of x. For that we should understand your e of x very carefully. Now what we do is we take one by one. First of all, we'll take single bit errors in the stream. If you have single bit error, what could be the error term we will see? And we'll ask Mr. Generator, are you going to divide it or not? Okay, if really that single bit errors, whenever error term represents single bit error, if that is divisible by g of x, then you are accepting the error, correct? So that's why in that way carefully we plan this g of x. Okay, don't worry, you will understand everything after 5 minutes. First of all, learn what is error term for single bit error. Let's take a single bit error intentionally, 10110, whatever it is. Okay, now g of x I am not fixing at this moment, but only code word I am fixing. I got this code word and I sent through the line. I got a single bit error at this position. Okay, 1 become 0 and 0 1 1 0 as it is. That's why it is single bit error, not burst error, correct? Now, what is the error term? Already I told you, when there is only single bit error, that means wherever there is a transition, wherever there is a tuple, you get one term in the error, correct? So now error comes into the picture, and error polynomial is, according to our shortcut, very simple, because 1 is becoming 0. What is the position? X power 0, x power 1, x square, x cube, x power 4, right? So definitely it is x power 4. Otherwise you can check it out. Write actual keyword, actual word in the polynomial model, and write false word in the polynomial model, and write false as c of x plus e of x. Okay, so c of x plus e of x is now actually your false word f of x. Then what do you want? E of x. Then simple, it should be f of x minus c of x. But f of x minus c of x is nothing but f of x plus c of x, because in polynomial addition, especially in modulo arithmetic, addition subtraction are same. We have seen that. So finally f of x plus c of x. Just if you do this, whatever you get, that is error term. In that way also we can do, right? Now let's check it out whether it works or not. So what is code word polynomial? x4, x cube, x square, x1, x power 0. That means code words formula is x power 4 plus x square plus x power 1. I am adding code word plus your false word. What is false word or transferred word? X power 0, x power 4, x cube, x square plus x power 1. Add them, you understand. So x square will be cancelled, x power 1 x power will be cancelled according to polynomial theory. So that will be the error. So finally I don't do all this stuff from now onwards. Directly I say that this is the error, right? Wherever there is an error, identify the position, that will be the error term. Understand? Now if you have 2-bit errors, what happens? We'll see. 1 0 0 1 0 0 0 0. Now see, there are 2-bit errors, right? X power 0, x power 1, x square, x cube. Then error term is directly this one, x cube plus this one, x power 0. That is what the error term. Now in that way, effectively, easily we can find out the error term, isn't it? Now let's focus on single bit errors. Whenever you have single bit error, then the representation is x power dash. Only one term will be there because only one error. But x power dash, it was x power 4 in the previous example. But generally what it is? So it depends on the ith position. If the position is I, okay, the error at ith position, then it will be x power I. Where positioning starts with 0. That means, positioning is like this, 0, 1, 2, 3, 4, 5, 6. Let's take like this. If your positioning is like 0 to 6, I'm assuming like that, then this is, let's say, bit 1 0 0 1 0 1 0. This is your code word. Okay, now let's show error here, 1-bit error, 0 0 0 1 0 0 1. There is a single bit error. Then we know that error polynomial will be simply, what is the position? 5, correct? X power 5. That is what I am saying. From now onwards, x power 5, x power I is the error term for single bit errors. Now the question is reduced to, example, whenever there is a error term, it will be x power I, correct, by g of x. The question is reduced to, Mr. g of x, do you divide x power I? If g of x divides x power I, such a g of x if you take, then that is useless. That means this g of x, we say that it is not able to identify this kind of errors because it is dividing. Whenever a polynomial divides error, then that circuitry accepts that it is correct because you are going to get syndrome 0. That's why. So we will not have any clue. To have the clue, so g of x should not divide x power I. Then 100% we can say that yes, there is an error. So finally, single bit errors can be detected by polynomials which cannot divide x power I, right? That's it. Remember it. I'm repeating it. Whenever a polynomial does not divide x power I, such polynomial can detect any single bit error. Let's observe some of the different polynomials as g of x. Example, let's say you have a single bit error, then x power I is the polynomial for it. Now, can we take your g of x generator as 1? No, 1 is absolutely false choice. 1 divides everything. So it is useless polynomial. We can't take g of x. So if you take g of x equal to 1, that means polynomial is simply 1, then it cannot detect anything. Next is g of x equal to x plus 1. So whether g of x equal to x plus 1 is a good polynomial or not, we'll see. That means, will it divide x power I or not is the question. We'll see. Really x power I is divisible by x plus 1, then we can write x power I as x plus 1 into some polynomial p of x. If you don't understand, I will tell you with one example. X plus 1 into, let's say, x square plus 1, you just multiply. What you get? You get x cube plus x square plus 1. That means x cube plus x square plus 1 is divisible by x plus 1, then we can write x cube plus x square plus 1 as x plus 1 into x square plus 1, isn't it? That means a polynomial is divisible by something, then that something should be factor of that. That's quite obvious, we know that, correct? In the same way here also, if x power I is divisible by x plus 1, then it should be factor of that, x plus 1 should be factor of that. So see, same thing, this is, let's say, x power I kind of thing, then if it is divisible by x plus 1, then we can write x plus 1 into other polynomial. So that is what I did. Now really it is correct. I am assuming that x plus 1 definitely divides some x power I. Then if I substitute x value 1, what should happen? We will see. If I substitute x value 1, a left hand side and right hand side you should get same values. Then only they are equivalent, isn't it? So let's substitute x value 1. You get 1 power I. In our polynomial multiplication, 1 power I is nothing but 1, correct? Because 1 into 1 is 1, 1 into 1 into 1 is 1. So let's substitute x value 1. Then 1 plus 1, 0. 0 into p of x, 0. In the entire story, I am using polynomial arithmetic and especially modulo arithmetic too, correct? Remember it. So 0 into anything is 0. Why you got different answers? Really x power I has a factor x plus 1, then this right side will have remainder 0, but left side always you are getting 1, right? This entire story can be explained with very simple concept like this x power I. Really x plus 1 divides something, then if you substitute x value 1, in our polynomial arithmetic also we do it, I will tell you that. See, because this is 1, right, take this 1 and substitute here 1. 1 power I is 0, then only x plus 1 divides it. The reason is very simple. In our arithmetic also, if you have x square minus 5x plus 6, then if you divide it into, otherwise if you factorize it, you get x minus 2 into x minus 3. So x square minus 5x plus 6, if you want to know whether it is divisible by x minus 2 or not, of course it is correct. But if you really don't know that it is divisible or not, then what we do? We take x minus 2 0, then x equal to 2, we substitute x equal to 2 here. If 2, if I apply 2, x square minus 5x plus 6 is 0, then we say that x minus 2 is a factor. Same thing we are doing here also. That means if you want to know whether x plus 1 divides something or not, then substitute 1 into that polynomial, and if you get remainder 0 or if the summation gives 0, then it is divisible. Example, my doubt is x cube plus x square plus x plus 1. Is it divisible by x plus 1? Simple. Substitute x value 1. 1 cube plus 1 square plus 1 plus 1. 1 plus 1 0. 1 plus 1 0 0. That means definitely x plus 1 divides it. If you have a doubt, just check it. I mean already we have seen, correct? Now one more. X power 4 plus x square plus x. This is divisible by x plus 1, yes or no? No. The reason, when you substitute x value 1, 1 plus 1 plus 1 is 1. So it's quite obvious to understand, correct? So finally, so if you have still doubt, just divide and check it out like this. You know the division process. If you do, then you get some syndrome. So finally, moral of the story, x plus 1 cannot divide x power I. That is done, right? Second thing, what x plus 1 divides, if you want to know, then simply substitute x value 1. Now, one important observation is, example, any error term, if your error is e of x equal to something like x power 7 plus x power 5 plus x power 6, okay? Now, this kind of errors cannot be, definitely detected by your x plus 1. Why? We definitely divide first of all by x plus 1. Then we substitute x value 1. 1 plus 1 plus 1. You get remainder 1. That means it is not divisible, isn't it? So x plus 1 is not dividing this one. Then really if you use this as polynomial, otherwise generator, then it will detect it. So error will be caught. Error cannot be caught when that error is divisible by g of x. You know that, correct? Now summarize. So finally I can say that x plus 1 can detect this kind of single bit errors. Next, it can detect 3-bit errors also. Whenever you have a 3-bit error, what happens? There will be 3 corresponding terms because there will be 3 togglings, right? Maybe 1 to 0, 0 to 1, 0 to 1 eventually somewhere, right? This is 3-bit error. See, bit number 1, bit number 2, bit number 3 in your sequence will be modified. Whenever you have exactly 3-bit error, then the corresponding e of x will be, example, the position, this one is 7th position, this is 3rd position, this is 1st position. Polynomial will be x power 7 plus x cube plus x power 1, doesn't matter. So how do you know whether it is divisible or not with x plus 1? Substitute x value 1, then you get 1 plus 1 plus 1, which is 1. Whenever you have error term with 3 terms, then that cannot be divisible by x plus 1 because you always end up with 1, right? Now if you have even number of terms in your error, example, your error is like this, x power 4 plus x power 2 plus x power 0 plus x power 6. If this is your error term, then when you substitute x value 1, then every 2 pair will be cancelled out, right? You get 0. That means such kind of errors will be divisible by x plus 1 and your x plus 1 cannot detect it because it says that yes, I got remainder 0. So whenever you get remainder 0 with divisor, there are 2 cases. That may be error may be cheating you, correct? Otherwise really error is 0. If there is no error also it is divisible. If there is error also sometimes x plus 1 is dividing finally, so that we cannot detect. Now summary, x power I we can detect with x plus 1. Second one, any even number of errors we cannot detect. but any odd number of errors we can detect. But one important thing is we should know whether this x plus 1 can detect burst errors or not. So burst error can be of even length or odd length, correct? What if your burst error has even length? Then it cannot detect. Odd length, it can detect. Correct? Then with respect to probability, anything is possible. Your error may have 50% of the time even terms. If it is a burst error, 50% of the time the error will have odd terms, right? If uniform distribution, if I assume, that means everything is equally possible. Then 50% of the time only x plus 1 is detecting the errors, and remaining 50% of the time it is not able to detect the error. That's why this is not a good polynomial, isn't it? So that's a problem. We have to identify the right polynomials. We will see that. Now we'll see x cube. So what is the capacity of x cube? We'll see. Can we use x cube as generator? Let's say your binary pattern is something 1 0 0 1 0, whatever it is, and at output side or receiver side, let's say you got 0 0 0 1 0. That means there is a single bit error, and we know what is the error term, right? Now we have to focus on only error term, correct? If you can divide error term, then that is not a good polynomial. So x power 0, x power 1, x square, x cube, x power 4. So this is the bit difference, right? So error polynomial is x power 4. Now x cube easily divides x power 4, right? That's why now syndrome will be 0. I don't know whether really there is an error or not. If there is no error, syndrome is 0. After error also, now this error is x power 4, then still your syndrome is giving 0, then we can't identify. That's why x cube cannot detect this kind of single bit errors. So how can you summarize it? Very simple. So x cube divides x power 4, x power 5, x cube, x power 6, everything, right? So that means, so whenever there is a single bit error at 4th position or 5th position, if you see, then definitely it can't detect. At 4th position also it can't detect. That's why 4th position, this represents 5th position, 6th, 7th, everything. So your polynomial x cube cannot detect any error which is occurring at 3 or 4 or 5 or 6 or anything. That means, so it is very weak polynomial. Easily we can understand, correct? Any single bit error it cannot detect if it occurs after 3rd position, or otherwise equal to, the 3rd position means, so here this is 0th position, 1st position, 2nd position, 3rd position. Then if error occurs at 3rd position also, it cannot detect. Understand? Let's see x plus 1 one more time. So this x plus 1 has one more problem. It cannot detect two single bit errors, otherwise double bit error, which is occurring contiguously. Example, see the situation 1 0 1 1 0 1, and exactly 2 bit error is occurring and it is continuous like this. Hey, example here, if you get 1 0 0 0 0 1, then this is the 2 bit error. Now what is the polynomial for the 2 bit error? That means e of x. Simple. This is 0 1 2 3 4 5. We know that error will be x cube plus x square, right? So whenever you have two errors like this, then that polynomial will have x plus 1 as factor. I can take x plus 1 factor, x plus 1 into x square. Just check it out. X square into x cube plus x square into 1 x square. That means what? So your error of x has a factor x plus 1, then x plus 1 divides it. Then again you can't detect. That's why, so x plus 1 cannot detect 2 bit errors which are occurring consecutively. If they are distributed, like one error at x power 7, one error at x power 20, that might get detected by your x plus 1. But if they are contiguous, like x power 20, x power 21, then error term will be x power 20 plus x power 21. Definitely I can factorize such a way that x plus 1 is one of the factor. So that's why x plus 1 cannot detect two single bit errors which are occurring consecutively, right? So that is the capacity of your x plus 1. Now we'll see some sophisticated polynomials. X plus 1 is not good, we have seen. Now x cube also not good. So any x power, some simple x power k is not good, right? X plus 1 also not so good, right? Then what are the good polynomials? We will see. So before going to that, first of all we will see some 2-bit errors. What is the structure of 2-bit error? If really 2-bit error occurs somewhere, like but need not be contiguous, then what kind of error term you get, we will see. 101101, and let's see here 120 0110, exactly 2-bit error. Okay, so also known as double bit error, double bit, then 1 becomes 0. See here, one difference here, one difference here. Then what is the error polynomial for this one? It's very easy. For that you should know the positions: x power 0, x power 1, x square, x cube, x power 4, x power 5. So it would be x power 5 plus x power 0, 1. So finally x power 5 plus 1 is the error. Then your polynomial should not divide it. If any polynomial does not divide x power 5 plus 1, then it can detect this error, right? Now let's generalize it. Any double bit error will have two terms. Sir, why here it is x power 5 plus 1? Because error at 5th position and 0th position, correct? 1 means x power 0. Similarly, if there are two errors, one is at, let's say, ith position, let's take this as jth position, and one error at ith position, then still this is a 2-bit error. Then what is the polynomial for that error polynomial? X power j plus x power I. Remember it. That means any 2-bit error can be represented as x power j plus x power I, where j comma I indicates the positions, right? So j is the jth position, I is the ith position, and my position start with 0. Remember, I am not numbering from 1 2 3 so on. I am numbering from 0. 0th position means first position. That means from right side to, if you go left side, then the first one is 0th position. So now you understand the structure of double bit error, right? X power j plus x power I. So here j is, notation is like this: j greater than I. Okay, now I can do some simplification here. Since I is smaller number than j, then I can take x power I common. Then what you get? You get x power I into x power j minus I plus 1. So finally double bit error has an error polynomial such a way that it is nothing but x power I into x power j minus I plus 1. So you know the significance of I, correct? So this I is nothing but, that is the starting position from right to left. If you go, see, from here to here while you are going, I is the first position where you got the error. Then second error is at j. Okay. Now example, there is an error at 3rd position, there is an error at 20th position. Then what is the error polynomial for this one? So 0th position is there, first position, second position, 3 up to 20, right? Then according to this equation, it will be, the error polynomial will be x power I 3 into x power j minus I 20 minus 3 17 plus 1. So this is the way we can represent any error. Understand? Now if there is an error at 2nd position and 14th position, so very simple, x square into x power 14 minus 2 12 plus 1. In that way we can represent. So now we can easily analyze this error term, and we can see the capabilities of all the error polynomials which can divide or which cannot divide these polynomials. We will see that. First, you remember at this moment, any 2-bit error can be written as x power I into x power j minus I plus 1. Okay.